Hey everyone, I'm Let's Farm. Welcome to Let's Debate. This is my co-host Sweet Pea, and we will be your moderators for this debate. Our topic tonight is go ahead. Our topic tonight is developing a bridge between physics and math important for young quantum engineer wannabes, and this promises to be an excellent debate. We have Void arguing that building a bridge is important, and on the other side we have UniLooK bringing the opposition. We will be having up to a 10-minute opening per side, up to an hour of open dialogue, and a short closing statement followed by audience questions. Remember to tag the moderators or Let's Debate with your questions for our debaters. Please remember to hit that thumbs up if you like the show, and don't forget to subscribe for more great content. Little reminder to attack the argument and not the debaters or each other. Now, since you are not here to listen to me ramble on, let's get to the show. Void will be going first, and Void, the mic is all yours.
Okay, I will be short today. I actually don't really know what to say because when we set up the debate, it seems a pretty open topic. I said my stance will be I have no idea how to become quantum engineering professional without understanding calculus, and my opponent said they will take the other side. So I think we should have clarified what quantum engineering actually means, but to me, it means to apply our knowledge about quantum nature of the world to build machines and various devices to solve real life problems. And the reality of modern day quantum physics is that it requires a lot of math. For example, Schrödinger equation is a differential equation, and the wave function, which lies in the very core of quantum physics, basically expects quantum operators to be applied upon it to get any connection to the real world we can observe and measure. So it's possible to get some isolated cases when, for example, you are a very junior amateur in some specially peaked field like quantum computing specifically, then yeah, you can do some useful engineering without understanding calculus. But if we talk about professional level and quantum engineering in general, then you do need to understand the underlying phenomena. Um, yeah, I can talk about what calculus provides for quantum physics, but I guess it will be a bit boring. Another important note to make here, I do not exclude the idea that in future we will invent new math, uh, and we will explain quantum phenomena in a much simpler way, so that it would not require this heavy math to be applied to understand quantum phenomena. But by this very moment, we unfortunately need to apply this math. Um, yeah, that's it.
All right, thank you for your opening statement, Void. And now we turn to UniLooK for his opening. Take it away, UniLooK. Mike's all yours.
Okay, well, it is true that physics and math is both are very important for becoming a quantum engineer, let's say. However, I think that while quantum mechanics can be a very challenging subject, it is possible for individuals who may not be particularly strong in physics to become quantum engineers. So they can be good at math. Um, they can be good at math, but I think it is actually possible to become a quantum engineer without a very strong background in physics. So here's a few reasons why. First of all, um, there's thing called collaborative environment. So quantum engineering is a very big field that involves physics, mathematics, computer science, and engineering, and whole other science subjects. And as a result, quantum engineers often work in teams and collaborate with others who have different areas to expertise. So, for example, if your friend is very good at physics and you're very good at math, you can always work together to become a very strong quantum engineers. However, you don't need to actually build a bridge between the two because, uh, well, you're only good at what you're good at. So the second point I'm making is focus on application. So that means that quantum engineering is a field that is focused on developing practical applications of quantum mechanics. Um, so while a strong understanding of underlying physics is certainly beneficial, um, what is often more important is the ability to translate the theoretical concepts into practical applications. And individuals who may not be particularly strong in physics, but have a talent for problem solving and innovation may excel in quantum engineering. And the last point I'm trying to make is accessible resources. With the growing interest in quantum technologies, there are now many resources available to individuals who want to learn more about quantum mechanics and quantum engineering. They may include online courses such as YouTube, Instagram, etc., and workshops, conferences worldwide. They are all accessible to anyone with an internet connection or have enough money to travel and attend those lectures. And there are even resources specifically designed for individuals who doesn't have strong background in physics. Um, so, in summary, while a strong understanding of physics is certainly helpful in quantum computing or engineering, it's not necessarily a requirement. So, that means that you don't really have to build a bridge between the two because physics is an engineer with only mathematics. Thank you.
All right, thank you, UniLooK, for your opening. We will now move into the open dialogue where our debaters will have up to 1 hour to cross examine each other. Debaters, please begin.
Okay, so from your statement, I don't understand how exactly quantum engineering professional will work. Because do you think understanding wave function is important for quantum engineering professional?
It is, yeah.
So how you apply wave function without understanding differentials and things like that?
I think that, well, first of all, um, differentials are in mathematics, and I'm talking about how you can excel at quantum engineering without having a strong physics background. Uh, wave wave theories are often really easy to understand. They don't necessarily require basic uh, physics knowledge to say, and yeah, that's my point.
The problem is to understand any phenomena in quantum world, you need to apply some operators to wave function. For example, if you have an atom of hydrogen and you want to understand electron orbitals, atom orbitals, I guess in English, the term. So you will apply this, so you will apply basically the energy operator and you get Schrodinger equation, you will get different energy levels, you will get the spherical function and things like that, and you will understand how this electron probability cloud work around the nuclei. And based on that, you can understand how this electron will behave in magnetic field and things like that. And from that, you will derive actual quantum phenomena. And this requires a lot of heavy math. I mean, like really heavy math. People who go, I think like the most people who go to the university would not be able to do that. So I don't understand the idea that wave theories could be understood as is without like heavy math and a lot of background here, and without creating bridge between math and physics and engineering.
So while wave function, as you've said, is a very fundamental concept in quantum mechanics or quantum physics, and although understanding wave functions may seem a daunting with a strong background in physics or math or whatever, there are some basic concepts that can help you grasp the idea of wave functions. In simpler terms, a wave function describes the probability of finding a particle at a specific location and at a specific time. Um, it's represented by a mathematical equation which contains information about the particle's position and momentum and energy and other um, properties. And the wave function can be used to calculate the probability of different outcomes when measuring some probabilities of particles. One way to understand the concept of a wave function is to think of it as a mathematical description of the wave-like behavior of particles. And okay, let me just give an example. In classical physics, particles are described as like point-like objects with um, definite positions and definite momentum. However, in quantum physics, these particles can exhibit wave-like behavior, meaning that they can be in different places at once, which is a superposition, and have uncertain positions and momentum until they are measured. And um, uh, it can be helpful to think these particles as mathematical descriptions of probabilities of finding particles. And um, yeah, that's my point.
Like there are two things here. First, yeah, of course I understand where it comes from, like this probability idea. But in the end of the day, wave function is complex function, while probability is described as real numbers. So it's not actually probabilities. It just when you get it squared, this manifests as something you may interpret as probability. But what is it underlying? We don't know, but okay, it's not required for engineering. For what is required for engineering is to be able to predict the behavior. For example, you want to use quantum tunneling. To use quantum tunneling, you again need to apply operators to the wave function to get probability that with these conditions, your like particle will appear on the other side of the barrier. So you cannot be like you can rely on hunch and try like just experiment until it starts working, but this is way amateurs work. It's not how professionals work. Professionals are able to exactly predict what will happen, and they're able to calculate the exact probability that this will work. And to do that, you do need to understand the again Schrödinger equation and all that math and all other applications of wave function. I don't think you may have a simple workaround here. It would require to invent some other math so that you can express this physics in a much simpler way and create intuition so that you don't need to use this heavy math. But we are not there yet. We haven't invented this. Feel free, by the way, to interrupt me if I talk too much. But that's what I would say on your point.
Okay, I really do understand your point. Um, my counter statement is uh, okay. Let's say that let's not talk about like professional um, quantum engineers because they are actually very good at both physics and mathematics. I'm talking about how you can be an amateur quantum engineer without having a really strong background on physics or maths. And I think it's very possible if you really do excel at one thing. So, for example, um, uh, okay, let's say you know qubits, right? They are particles that um, transfer information in quantum computing. So uh, let's talk about polarization of qubits. Let's say you have a really good background at physics, but not as good as a background on mathematics. Uh, you can actually understand the um, theory behind um, polarization of qubits and how it can um, transfer information using probabilities and stuff uh, without having a really good background at mathematics. Um, because polarization of qubits is a really similar to compare to polarization of waves, which is also really easy to understand if you excel at physics. Yeah, that's my point.
Uh, when you sorry, just when you say the word, it is parallelization, not polarization, right?
It is polarization.
So when you have when you have a lot of things parallel, or when you have poles.
Pulse, like
Okay,
when
okay,
qubits travel through like a tunnel. No, let's say when qubits exist normally, they are actually very indefinite particles where we don't know their position or the momentum and stuff. However, with the theory of polarizing those qubits, you can actually transfer information really easily. It's just like polarization of waves, where when light waves travel, they are non-polarized, which means they travel in different directions. And when you polarize them or make them in one direction, you can actually okay, sorry, you can actually absorb some great results from there.
okay. So basically, your point is it's quite easy to intuitively understand like what is qubit and what logic you can build on top of qubits. That's your
Hmm.
point, right?
Hmm.
Um, okay, so so we go into quantum computing basically. Yeah, in my opening statement I said that you can like cherry pick specifically some narrow areas of quantum computing and do stuff inside this specific field without like a huge math understanding, but it works so far. I mean, it doesn't work too much. I mean, you will be able to reproduce existing algorithms which are already published. You will be able maybe to understand some of them. I mean, fundamentally what they do, but not all of them. But if you will be able, but if like you will try to solve real life problems, um, uh, uh, yeah, like it's not requires some differential equations or things like that, but it requires pretty good training in discrete math, like in a lot of different math, so that you can create your own algorithms useful for like real life world. uh, this is like one thing.
Okay, I'll try to
Okay.
defend my point here. You said that uh, it is actually possible to understand some of the algorithms, no?
Yes.
So isn't that uh, really really an enough requirement for becoming a amateur quantum engineer?
I guess. Uh, yeah, I guess like quantum engineering is a broad topic. You can be an amateur quantum computing engineer, but very, very junior amateur. Yes, here I agree. Uh,
Mhm.
uh, like, but this is like,
Well,
I would say, an exception through the whole quantum engineering.
um, it is actually the same for the maths. Well, if you excel at math and you're bad at physics, you can actually develop really hard algorithms without needing to step into the physics world. And you can actually apply those algorithms to, let's say, if you have a basic understanding of qubits, you can actually apply that algorithm to those basic understandings and create your own algorithms. I I think so.
Uh, like the main problem, I guess, here is that when we talk about quantum engineering, we usually do not talk about quantum computing specifically. Quantum computing is like 1% of all quantum engineering, or even less. We like still have a very small in terms of amount of qubits computers and quantum computers, and those computers are limited in how these qubits could be used and things like that. So basically we talk about very small amount of engineers who work actually in this area. Uh, but when you, for example, want to build an MRI machine, which requires a lot of quantum engineering, you just cannot get rid of classical universal university education. From my point of view, at least I don't know any other way. uh, Maybe somebody could propose another way.
Um, well, I agree that high-level engineers do have do excel at both of the subjects. Um, However, the point I'm making here is if you excel at one subject and you're bad at the other, you can actually use it as an exception to, um, you know, developing a, let's say, a good, um, uh, I, my English vocabulary is not as good. However, okay, the point I'm making here is you can actually grab a field that is in quantum engineering. You can actually grab a field that fits for you, uh, for your requirements. For example, if you're bad at physics and good at math, you can grab this field in quantum engineering. However, if you're good at physics and bad at math, you can grab this field in quantum engineering. Yeah.
I don't think if you like exclude quantum computing, then there is any other like at least in quantum physics field where you can work without math. So when you say good at physics, bad at math, I don't think that's even possible. uh, and uh, you were saying like this case where you have a team, a mathematician and physician, not physician, physicist. So like basically in this team, the physicist will be just dead weight. They will do nothing because because any action from quantum physics would require heavy mathematical operations. And quantum computing is an exception only because basically this is like computing. So, but we have classical computing where we have no restrictions on information should be preserved and things like that, while we have quantum computing with the other computational rules. And because of that, it's not it's not physics anymore. It's actually just like quantum computing, not physics. But if we talk about physics, I would love to hear any example where you can be good without math.
Well, let's say quantum optics. You can be good at quantum optics without needing a very strong background in math. You know.
Quantum optics. I'm trying to understand. What is quantum optics? Sorry for my ignorance.
So I'm trying to make this easier for understanding. So it's like an subject that studies the uh, interaction between light and matter. You know, light and state of matter in quantum level. So it combines the principles of quantum mechanics and electromagnetism to describe the behavior of light. And yeah.
How it differs from classical optics? Would you give a simple example so that I understand what we are talking about?
So quantum optics, there are several areas in quantum optics, which include quantum information processing, where the researchers aim to use properties of photons to perform calculations and transmit information, and quantum coherence and decoherence, which describes how quantum systems can lose their coherence over time um, due to interactions with their environment. And these areas, uh, okay, let's say quantum coherence and decoherence, they really don't need a very strong background in mathematics.
Okay, so you say coherence and light and things. So I guess lasers are inside this area, right? Or
Yeah,
no?
I guess you could say that.
So how could you build laser without understanding of energy levels of an atom, and how you can understand energy levels without understanding again Schrödinger equation and without math?
Yeah, yeah, basically.
So you say that that's possible just to ignore Schrödinger equation, just like and build a laser.
Yeah, I think it is possible.
I think you would need to rely on work of other people who tried to apply quantum physics to real world and already laid out all the engineering work for you, and you just repeat what other people did. It again, yeah, okay, this is good enough for amateur, but not good enough for a professional. So if you want to stand for amateur thing, yeah, I guess you could do some experiments. You just cannot do anything useful for the humanity. Uh, so I guess there is the border.
Mhm. So you're talking about Schrodinger's equation, and
Yeah.
I agree that basic understanding of Schrodinger's equation can be helpful in studying quantum coherence, but I don't think it's strictly necessary. And quantum coherence, like as I've said before, quantum coherence is an ability of a quantum system to maintain its state over time, and it's a really fundamental concept in quantum mechanics. However, um, there are some frameworks and approaches that can be used without relying on Schrodinger's equation. For example, um, the to use the language of quantum information theory, which describes the coherence uh, in terms of entanglement and other quantum correlations. And other approaches can include um, this. Okay, I don't know if I'm saying this wrong, but density matrix. I think that was it. And it can be used to study coherence in quantum systems where system is interacting with its environment and is not isolated. So it's strictly based on pure physics, not uh, diving into like advanced mathematical equations and stuff.
Um, First of all, I want like just to nitpick. I do mistakes, but just to nitpick to what you said. I would say that coherence is not about ability to preserve itself with time, but more about that frequencies are aligned between two wave functions, and so they can interact with each other. They are not. So when you so again you need math. Even I need math even to understand, to even to explain what I want to say. So what I want to say, when you do integral for some interval of two functions, and if you want them to interact with each other, so that like multiplication of them under this integral won't be zero, you need them to have some shared frequencies or things like that. And in my mind, quantum coherence is more about this rather than ability to preserve itself. Um, about that was nitpicking. It's not like against your point. I was just corrected. About your point. So you say it's possible to avoid like Schrödinger equation by using density matrices. Have I understood you correctly?
Yeah.
Sorry, yeah, like my education ended like, I don't know, a lot of years ago. I forgot things. What is density matrix?
Um, Again, I'm a high school student and I'm just starting to understand this concept,
Okay,
but um,
let me Google quickly, a few seconds. Operator, it matrix that describes quantum state, blah, 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 blah.
it's like
Advanced measurement.
a generalization of wave function. It's like
Yeah, but
matrix
it's
with
again
yeah,
it's
it's
again
like
an operator.
yeah, it's like a matrix with complex elements that um, gives out all the probabilities uh, of measurements or like possible outcomes of measurements.
Okay. Yeah, I cannot actually answer on this because I need to like spend a few minutes reading. So you say that there is like quantum optics. In quantum optics, you can go into some phenomena without understanding Schrödinger equation by replacing it with the density matrices. Okay, let me think.
I think it is actually easy to understand density matrix. It doesn't like require um, uh, heavy math.
Again, I don't understand. Like, you want to build a laser. You even want to like experiment on entanglement, and you want to build a laser, like propagate light for a few kilometers and experiment with that, like quantum optics, blah blah. But you want to build a laser. To build a laser, you need to understand energy levels of atoms so that you have this resonance inside your laser to gather a lot of coherent photons, to like a lot of coherent energy together, which will be emitted out of this laser. So, like, you either reuse what other already did, other already calculated which energy levels you have, how exactly you need to build a laser, and basically you do no engineering, you just like technician who just assemble things, or you need to be able to calculate these energy levels yourself. I doubt that you can do that through something like density matrix. I don't really know or remember what that is, but either density matrix should require a lot of math, or it should not allow you to calculate energy levels on an atom. Otherwise, in quantum chemistry, they would use it a lot. But I know for sure that in quantum chemistry, they have to do heavy computations with Schrödinger equation. So, okay, you. Could you give an example how you use density matrix?
Well, yeah, sure. Density matrix is like a, it's like a vector, and it actually, um, let's say, okay, so density matrix is like a study of open quantum systems where systems are interacting with its environments, and density matrix is like a state vector of the system. So for example, let's say a density matrix that's named alpha consists of two variables, and those variables are actually vectors of the quantum system. And um, well, it is used to describe the reduced state of the system, which is obtained by tracing over the degrees of the environment of the quantum state. So you can actually use those state vectors to calculate the um, uh, entanglements of those quantum states and other forms of quantum correlations. And it allows you to describe the correlations between two systems of two quantum systems or two quantum subsystems, and etc. and etc. And yeah, that's how you use it.
But in density matrix, do you have real numbers or differential operators, or what are like items of this matrix?
So they're like state vectors. So yeah, they're basically numbers.
So inside each cell or element of matrix, you have vector,
Yeah, vectors.
but this vector contain inside real numbers, right?
I think so, yeah.
Okay, in this case, it looks like density matrices are could be used in very limited applications. So, only for those quantum systems which you can fit into this pattern, uh, because there are like complex quantum systems. For example, if you take atom of helium, it's not expressible in this format. Uh, you and again, if you do build a laser, you again uh, need to calculate upon complex quantum state, which could not be expressed as a bunch of real numbers inside vectors inside of matrix.
Yeah, I agree. However, again, my point I'm making here is you can actually choose from the fields that are available in quantum physics, or in this case quantum optics, that is fitable for your knowledge. So for
Okay.
example, if you're like really good at practical physics, you can um, like measure. You can be in the measurement field. For example, you can like measure the, I don't know, you can work in the laboratories and just measure things, and yeah.
Yeah, okay, I agree here. You can find some cases where math could be like drastically reduced to something like matrix you mentioned, and in these specific cases you can do calculations much easier and derive some conclusions much easier. Okay, I agree. You can do some amateur stuff in here. You cannot do any professional stuff in here. But like the fundamental problem here is that you again go to things which lies as much as possible to quantum computing. You try to like pick the area where your quantum system is simplified so much that your activity is not focused on physics, but focused on manipulating these reduced states, as in quantum computing. Uh, so I don't know. It feels very narrow to me. Like, um, let me give you an example. Though I already gave with quantum tunneling, but let me try to imagine another example. Um, even like even without quantum physics, even again if we go to MRI machine, to use MRI, to build MRI machine, you need Fourier transformation, and Fourier transformation is again like in continuous numbers, it implies integrals and things like that. So like when you try to build at least something useful for humanity, you always get stuck with this heavy math. Uh, so, um, yeah.
Yeah, I agree. If you want to be like a professional engineer in a very complex field of um, quantum engineering, then you do need both of the physics and math knowledge. Um, yeah, my let's just say my last defense here is that um, my last defense here is that whether you have a strong knowledge base on physics or a strong knowledge base on math, you can always find a fitting quantum field that is fitting for your knowledge base. And yeah, that's my last defense.
Uh, okay,
Uh,
I guess we have some kind of agreement. So basically, you say there are some areas in quantum physics, at least they considered to be uh, yet considered to be parts of quantum physics where you could do something without difficult math, but at the same time it will never be professional activity, uh, and the most of these cases built on top of idea reducing quantum state to something very easy, like binary state is with qubits, or like these quantum matrices, or things like that. So yeah, I guess this is the border we achieved, and I agree this is kind of the border. uh,
yeah, I also agree. Um, I, I think we should like wrap this up. No.
All right then.
uh,
Are
yeah,
you guys finished?
yeah, I'm thinking like, do we have any unclosed topics here? Few seconds. Yeah, I guess there is nothing else to discuss here.
All right, then, we now come to the close of our debate. We'll let each debater make a short closing statement if they choose to, and then we'll move on to the audience questions. Since Void opened first, we'll let UniLooK close first. UniLooK, anything you want to say?
Yeah, sure. So I've come to the conclusion that while um, knowledge base in physics and knowledge base in math is very necessary if you want to pursue your career in quantum physics. Um, I don't think it is necessarily a requirement because you can always work in a field that is fitting for you and your knowledge base.
All right, thank you for that, UniLooK. Now, Void, would you like to make a short closing statement?
Yeah, I think like the whole thing goes from the fact, I'm assuming that's how I feel, that UniLooK has exposure to quantum computing specifically. And quantum computing is different from quantum physics. It's considered to be a part of quantum physics, but like people play with very different rules in that field. And maybe because of that, we have this conversation. It feels to me, maybe I'm wrong. But I agree with like the how to say with the um, effort to find easier ways to use our knowledge. Right now, quantum physics requires like a lot of study to just start doing very simple things, and this is a problem. Somebody should invent simple math or simple methodology how to use quantum knowledge about quantum nature of the world and things like that. And it is nice that like we discussed that. And I think one of the major problems why people don't know quantum physics is because like in other areas you can gradually learn, you can learn some bit and you can apply it, you can learn a bit more and apply it. Quantum physics in general is not that, and maybe because of that we don't have much quantum engineers. So if UniLooK will success in future in proving that quantum physics could be like used without a lot of math, I would be very happy, but it feels like we are not there yet. That's it.
All right, thank you, Void, for that. Now we're going to move into our audience questions, of which there are two. The first question from Bruce6 for both of you. Are you both atheists?
I'm agnostic.
I'm well. I'm gonna say I'm Muslim.
Okay, then. All right, thank you. And our next question is for me. I have a question for you, UniLooK. Are you going to pursue an education in physics?
I am actually planning to pursue my education in physics. I'm planning to work in an MIT lab or a lab in IBM or Google, pursuing in quantum physics or quantum computing specifically. Um, uh, the the real reason why I chose this topic is to prove that um, physics and math is both needed for quantum physics. However, um, you know, you gotta challenge yourself sometimes, and this was really hard because I do understand that physics and math is really needed. However, I need to defend my point, so that's why I made different counter statements. Yeah,
Well, thank you for answering that. Congratulations and good luck in your future educational pursuits. That's a tough field you're going into.
thank you.
All right, and I'd like to thank everybody for coming tonight or today, and I hope you enjoyed our show. We will be adding your guys' links to the description. If you have them, please DM them to me. And if you liked your performance here, please consider subscribing to their channels. Remember to hit that like button if you like the show, and also consider subscribing to our channel and hitting that bell to make sure that you do not miss any of our exciting content coming up. Thanks again for coming. Thanks to our debaters. Thanks to my fellow mods. And Remember, let's not fight. Let's debate the topics and let's talk about the issues. Thank you all again for coming. Anyone else?
Thank you for having me on this debate.
Yeah, thank you, UniLooK, and the hosters for this debate.
Absolutely.
You're welcome.
Everybody's welcome back to do this again if you ever want to. All right, I'm going to close this up. Let's say goodbye to everybody. All right.
Bye, everyone. Thank you for
Bye.
being here.
Thanks for
Thank you
coming.
for hosting Let's Farm.
All right. Good night, good afternoon, or good evening.